We are continuing our study of function analysis, and in this video we are going to take a look at concavity and points of inflection. Let's take a look at this interesting graph again. This is the graph of what we are calling f of x, and concavity is an aspect of a graph that is easy to see when you're looking at a graph. F is said to be concave down on sections of the graph, intervals of the graph, where it looks like a frown. So let's see. This section right here does not look like a frown, does it? This section looks like a smile, right? Instead of a frown. This section, however, looks like a frown. So there is some point in between here where it changes from looking like a smile to looking like a frown. So the section of the graph that looks like a frown is where we are concave down. All right? Now, so I have a little rhyme here. Concave down looks like a frown. So where is it concave up? Well, the curve is concave up when the curve looks like the opposite of a frown, which you might say is a smile, which I like, but it doesn't rhyme. So I say concave up looks like a cup. I had a student a couple of years ago that came up with that, and I liked it because it rhymed. I still think of it as a smile, but whichever one works for you is great. So concave up looks like a cup or a smile, all right? It's a happy face. Concave up, you're cheering up, you're happy, right? Concave down looks like a frown. Okay? All right. A point of inflection is a point on the function where concavity changes from upward to downward or downward to upward. So the point where the curve changes concavity is called a point of inflection. Let's draw some tangent lines to this graph on a section of the graph that is concave down. So I guess I'll just pick this little section. We know that that's concave down. Let's draw some tangent lines. So at this point right here, the tangent line would be like there. At this point right here, that little relative max, the tangent line would be there, right? Here it would look like this. Here it would look like this, yeah? And so forth, okay? So what do we notice about the tangent lines where the curve is concave down? If f is concave down, the tangent lines are above the curve. So the tangent line would be above the curve on any concave down section of the curve. Similarly, if we drew tangent lines to a concave up section, all of the tangent lines would be below the curve rather than above the curve. So if f is concave up, the tangent lines are below the curve. It just makes sense. All right, definition of concavity. Let f be a differentiable function in an open interval, I. The graph of f is concave up on the interval when f prime, the derivative, is increasing on the interval, and concave down when f prime is decreasing on the interval. So let's take another look at that, okay? Let's take a look at this concave up. This little section right here is concave up, yeah? So I'm going to start right here. This point of inflection, if I draw the tangent line, part of it is going to be above the curve and part of it's going to be below the curve, okay? As we go to the right, this next little section, let's take a look. This next section here, it's going to be hard to see, but something like that. And then we would be here. These tangent lines, think of the slope of each of these tangent lines. The slope, this is a pretty steep negative slope, right? As we move forward, what happens to the slopes? The slopes all increase until we get to here where it's 0. It was negative, and now that the slope is 0, and then as we round this relative min, all of a sudden the slopes are now positive, and they get higher and higher and higher and higher until we reach that other point of inflection. So f prime is increasing when f is concave up. We use the little abbreviation CC with an up arrow. That's a little recognized abbreviation for concave up. Okay, so f prime is increasing when f is concave down. Similarly, when the curve is I'm sorry, I said that wrong. F prime is increasing when f is concave up. Similarly, f prime would be decreasing when f is concave down. So here, the slope is pretty high, positive number, and as we keep on going, the slope is getting less and less until it gets to 0, and then it becomes negative after that. And it keeps on getting lower and lower until we get to that other point of inflection, and then it's going to change and become increasing again where the curve is concave up. That is the definition of concavity. So if f prime is increasing, then what can we say about f double prime? Well, f double prime is the slope of f prime. So f prime is increasing when f double prime is positive. So f is concave up when f double prime is positive. That would be when f prime is increasing, when its derivative is positive. That's what we said for a function to be increasing. Its derivative is positive. So f prime's derivative is f double prime, so f prime is increasing when f double prime is positive. F prime is decreasing when f double prime is negative. And that is our test for concavity. If f double prime is positive for all x in some interval, then the graph of f is concave up on that interval. Okay, for concavity, unlike increasing and decreasing, for concavity we do not include boundaries. Okay, the test for a point of inflection then, f has a point of inflection at c f of c if f double prime changes signs. F double prime changes signs at x equals c. Note that the second derivative must change signs. It is not enough for the second derivative to be 0 or undefined. That is a common mistaken justification for a point of inflection that I have seen on too many students' papers. A function does not have a point of inflection because the second derivative is 0. That's true only in a polynomial, okay? Don't get used to that being your justification. I encourage you not to use it even as a even on a polynomial. Just figure out where f double prime changes signs. Okay, then it'll be good for every kind of function. All right, one more note. Also note that a point of inflection must actually be a point on the function. A point of inflection is a point. So if the second derivative changes at a value of x that is not in the domain of the function, it cannot be a point of inflection. Let's look at some examples. Let us consider this function. Now this is a polynomial, okay? And it's a negative cubic. Do you know anything about the graph of a negative cubic function? A negative cubic could look like this, like that, or it could look like this, where it just gets flat and goes down, like that. So in other words, it could have a relative min and a relative max, or it could have neither a relative min nor a relative max, just get flat in the middle. Let's discuss the concavity of H. So as soon as I see concavity, I think to myself, F double prime. F double prime is positive for concave up. F double prime is negative for concave down. That'll be our discussion of concavity. All right, so let's find H double prime. So first we'll find H prime, and then we'll find H double prime. So for H prime, this will be negative 3x squared, little power rule here, plus 12x minus 9. Take the derivative a second time, negative 6x plus 12. So since we are looking for when F double prime is positive or negative, we need to sign chart F double prime. For the sake of your notes, I'm going to write this. Sign chart F double prime. Okay? So we're going to find the values of x that make H double prime 0 and then put those on a sign chart. So I'm going to set this H double prime equal to 0. We're going to get x is equal to 2 there. Put that on a number line. We're testing H double prime this time because that's for concavity. To the right of 2, if I put something like 5 in, I'll have negative 30 plus 12. That's negative over here. On the other side, I know it's going to change signs because that 2 came from a single factor. So on the left of 2, the graph is concave up. On the right of 2, the graph is concave down. That makes 2 a point of inflection. They didn't ask about that here. I'm looking ahead to point B. That's going to be our answer in part B. So I kind of jumped the gun on that. But anyway, we're concave down, so I'm going to go off to the side here. So I'll say H is concave down. I'm going to abbreviate that. Concave up on the interval from negative infinity to 2. Okay? Since I almost said F, H double prime is greater than 0 there. Another way you could say negative infinity to 2 is just to say x is less than 2. Right? H is concave down on 2 to infinity, since H double prime is negative there. And of course here you could just say x is greater than 2. Alrighty? So we did that. We discussed the concavity of H, and we gave our reasons why we could discuss that. State the point of inflection. Points of inflection of H, if any exist. Justify your answer. Well, we already did all the work for this, so I'm just going to state my answer. H has a point of inflection Well, I didn't do all the work for it. I found the x value of it, so I'm going to start this at 2, and now I need to find the y value when x is 2. So in class I would say, which function do I put the 2 in for to get the point of inflection? So the point of inflection is on the original graph. It is not on the second derivative or the first derivative. In fact, if we put this number in for x, we would get 0. Okay? Not that there's anything wrong with 0, because that would make a point, but it's the wrong point. Okay? So we need to come and find h at 2 to get the h coordinate of that point of inflection. So I'm putting 2 in for x, so that'll be a -8, plus 6 times 4 is 24, minus 9 times 2, that's 18, minus 1. Let's see. I've got negative 26, negative 27, plus 24, that's going to be a negative 3, I hope. H has a point of inflection at 2, negative 3. We need to justify our answer, so I'm going to say since H double prime changes signs there. That will always be my justification for a point of inflection. Whatever function you're talking about, its second derivative changes signs there. How many points of inflection does f have if f double prime is this function? Well, they've already found, that was really nice of them, they already found f double prime for me. I don't even have to take a derivative. They found it for me. And it's already factored for me. So all I have to do is set that guy equal to 0. Okay, those would be the values of x that go on my number line. So x is equal to 0 from this factor, 2 from this factor, and 5 from that factor. Now, I do note that that 2 came from a double factor. So on the number line surrounding that 2, we will not have a sign change. In fact, I already know what my answer is. So let's take it another step here. We're looking at f double prime. If I go way out here, like to 10, positive, positive squared, positive, everything's positive. Surrounding that 5, we're going to have a sign change. Surrounding the 2, we will not have a sign change. If it was negative on the right side, it's going to be negative on the left side. Surrounding the 0, that came from a single factor, so we're going to have a sign change. So how many points of inflection are there? Well, there's one here, because we have a sign change. There's not one here, but there is one here. There are 2 points of inflection. Okay. Let's see. F is equal to this polynomial, where k is a constant. If f has a point of inflection when x is 8, then k must equal what? All right. Well, f has a point of inflection when x is 8. That means in a polynomial, that means that f double prime equals 0 when x equals 8. So that's going to be my key. I'm going to find f double prime, plug in 8 for x, and set it equal to 0. So f prime will be 3 times 1/6 is 1/2. Reduce our power. 2 times negative kx will be a negative 2kx. The derivative of 1 is 0. F double prime, 2 times 1/2 is 1. Decrease your power by 1. The derivative of negative 2kx, where k is a constant, is just negative 2k. And this is equal to 0 when x equals 8. So 8 minus 2k is 0. K is going to be 4. So there's a variety of problems that we can be asked dealing with concavity and points of inflection.